Okay, good morning. So, we will continue a quick tour towards the basics of quantum mechanics. So, and of course, apologies for everyone for whom this all is repeated. But uh, let's start. So, today we are going to talk about uncertainty, measurements, and basics of quantum mechanics. Okay, so well, the uncertainty principle, we already saw it in the double slit setup. Uh, we had paths, and we said that the uncertainty principle was one cannot determine which slit the electron went through, and also preserve the interference pattern at the same time. So, in some sense, the uncertainty principle is putting some sort of a fundamental restriction on the theory itself. It has nothing to do with your technology. It has nothing to do with that you're lacking something in your technology or your measurement apparatus or the way you cannot do it. And people have tried to overcome this guy, trying to preserve the interference pattern and also detect which path the electron took for 100 years. It's not possible. I mean, that's essentially what we believe. So, uncertainty principle, in some sense, puts a fundamental limit uh, on the information we can obtain about the system. And there are several ways of quantifying this notion of the uncertainty principle. And the most popular one is, of course, which you're already familiar with. And what does it mean? It means that one cannot define, this is the variance in x, this is the variance in the momentum. One cannot define position and momentum to an arbitrary precision. So, once again, uh, is it a limitation of the measuring device? No. The notion of well-defined position and momentum position and momentum simultaneously does not exist in quantum mechanics. So what is delta x? This was the variance, or the standard deviation, and delta p was similarly this guy. So these are statistical quantities with respect to what? With respect to which distribution? Well, that distribution actually essentially characterizes the state of the system, or in some sense, the state of the system is described by a distribution. And Heisenberg's uncertainty principle tells us what are the states permissible under this theory. And as you can say that, once again repeating, the uncertainty principle is something which is inherent in quantum mechanics. And we will see the power of the uncertainty principle. Now, we would use this limitation as a weapon for us, let's say, uh, intuitively in some sort of a cryptographic protocols, or we'll see how can we harness the power of the uncertainty principle. So this is something inherent in quantum mechanics and nothing to do with technological limitations. This is a fundamental restriction on the theory itself. Technological limitations. So, in other words, if you have a phase space with the momentum and position, well, this is how classical phase space looks like. You have a definite position and a definite momentum, classical phase space. Well, quantum mechanically, let's represent this by this notion of uncertainty. This is not a point, but there's a fundamental uncertainty associated with position and momentum. So I'm just representing it by a uncertainty cloud. Or in other words, delta x, delta p, if I have to plot, and let's say this is a hyperbola, delta x, delta p equals to h bar by 2. And then what do you think is going to happen? What are the which side of this hyperbola does the set of states in quantum theory look like? Whether it's these guys or it's these guys, including this curve, obviously. So the question for you is that where does uh, permissible quantum states lie? Which region? I mean, okay. So next we come to quantum measurements, or let's say measurements, and it's convenient to introduce measurements through polarized light. You have, let's say you have the incoming wave of the electromagnetic field. This is light wave, so essentially I can represent it by its polarization, and the real part of the complex quantity, let me call this guy. So let's say this is my incoming wave, and let the incoming wave pass through polarized glass. So let's say I have a polarized glass with, this is the direction of polarization, and I have an incoming wave call it. What happens? So the output, and you can do this experiment, output is going to be something polarized in this direction, and with an amplitude given by the dot product. Or in other words, if the angle between them is theta, let's say the angle between them was this was E in, and the angle was theta, we get E, this guy, and the intensity is just well, the modulus square of the amplitude, and it's given by a factor of cosine squared theta. So in a way, this is an example of a projective measurement. This is an example of projective measurement. The input gets projected in the direction of the output. What about single photons? We talked about the wave. What about single photons? Well, a single photon is either absorbed or transmitted. And the transmission probability is cosine square theta. So I have E in, E cosine theta. Very good. So now let us look at a measurement apparatus where I have an incoming photon and it can be a wave also, doesn't matter. Let's say this is my polarized glass, polarized in a particular direction. Well, E in can be in this direction. So that's the direction of E in, doesn't matter. Then I make it pass through this guy, horizontally polarized glass. This was a vertically polarized glass. And I ask you, what's the output? Well, the output you can see is blocked by cross polarizers. We can check it through our mathematics. The cosine angle becomes 90 degrees. So this is blocked by cross polarizers. What about a randomly polarized light wave, or wave having the polarization all over the place? What happens when I pass through this guy? Let's say this is an incident wave with a superposition in all possible directions. And what happens? So the intensity I pass a randomly polarized light with superposition, equal superposition in all directions through a vertical glass plate. In order to calculate how much intensity is passed through this guy, I need to calculate how much intensity is in the vertical direction. So for that I integrate the contribution of intensity and convince yourself that the magnitude of intensity is given by this guy in the vertical direction, and that comes out to be, after the integration, I by 2 pi well, you just do this integral, this comes out to be I by 2. So initially this guy was incident, and we calculated how much of the intensity passes through this, and then what happens? I have let's say I have another glass beam, glass circularly, I have polarized glass with polarization. Let me draw it better. polarize in this direction, pi by 4 to the original direction of polarization, what do you think will happen? Well, I'll get I by 4. You can calculate this. And then if I have another glass plate, so I'll again repeat the setup. I had an initially polarization which was a superposition in all directions. This was my first glass plate. This was my second glass plate. And this was my third glass plate. All at an angle of pi by 4 with each other. And I'll see that I'll have I by 2, I by 4, I by 8. But what happens in this scenario, scenario 2, let me call this case 1, this is case 2. What I'm going to do is I'm going to swap these two. Again, I had a randomly polarized light coming. Now instead of putting the vertically polarized glass plate first, I put one at the 45-degree angle to the vertical, and I put this guy over here, and I put again this guy. This plate remains the same thing. I just swap the first two plates. Now what's going to be the output? Final output. So you would notice that the final outputs, because these guys are at 90 degrees to each other, is 0. So just swapping two plates over here gives a totally different output than in the first case. This is a general message. What I wanted to give is that unlike classical operations, generally quantum operations like measurement do not commute. We will see, of course, this has profound consequences in quantum mechanics, and well, in some sense, you could also argue, based upon classical wave theory, that in this case, even the classical operations, you could have taken this to be a classical wave instead of a single photon bombing. So I can deal either with a single photon, and the idea is that the probability of detecting a photon after this thing is 0. Or I can deal it, I do the same sort of an experiment with a wave, and I would see that there is no intensity whatsoever. So in this case, you can also say that classical operations were not commuting, but you would see that this feature of operators or operations not commuting is a very defining feature of quantum mechanics, in the sense that you would see it more often, and we'll come to know how is it different than analogous classical counterparts. So in some sense, this was a very short overview what sort of things we deal in quantum mechanics. We talked about events, processes, probability, amplitudes, uncertainty, and measurements. So this is a good point to introduce a mathematical formulation, or put all these things mathematical formulation of quantum mechanics. Okay, so by the way, we talked about single photons, polarization, measurements. A challenge for you guys is to start thinking about a cryptographic protocol based upon polarization, the polarization degrees of freedom of a single photon. Do you think you will be able to send messages secretly just using the polarization degree of freedom? If then how? How you have a sender, Alice, you have a receiver, Bob, and you need to send secret messages, communication between them. How are you going to accomplish this task through polarization? Okay, so that was of some sort of an interesting digression. Okay, so we return to the mathematical structure of quantum mechanics or formalism. Well, we started by saying that essentially the idea of quantum mechanics is to solve for probabilities of outcomes and that led us to notions of probability, amplitude, events, so on and so forth. To make these notions more quantitative, we need a more formal way of treating uh, to make this quantitative. We need a more formal treatment of quantum systems. So essentially a quantum system is specified by a state vector. Uh, this is how I'm going to represent vectors. This is called the bracket notation, and this guy is called the ket notation, bracket notation. This denotes a vector in a linear vector space. Well, note this is not the most general state. Remember we talked about maximal information, giving the maximal information to the experimentalist. So if we have maximal information about the system, then it is described by a state vector. Well, the system, what is the system? Well, the system can be anything, and anything quantum mechanically, the system can be a particle, a galaxy, a dog, and essentially all the information about the system is in the state vector. We shall see how the state vector evolves with respect to time. Quantum mechanically, we have described the initial state as a state vector, and we are going to give rules of evolution, and that constitutes quantum dynamics. So what we have is again our beam splitter, and as we said, so let's say this is the way time is going. Just see it as a tilted beam splitter, so to speak. So the state vector alpha, beta entries gave the probability amplitudes of finding the photon in the upper or the lower beam. So I just call this as my state vector, and essentially this is what? This is this guy, where I have my basis vectors as everything in the upper node and 0, 1 as everything in the lower mode of either all the probability of the photon is in this mode or this mode, corresponding to two of my basis states. Now this quantity is nothing but just alpha, which actually is the probability amplitude of being in the one of the modes, and the amplitude square is the probability of detecting photon in the upper. So this quantity over here represents an inner product or multiplication of a row vector with a column vector. And in general, you can have the basis states in a higher dimension system, and the probability amplitude is given by this inner product. So the interpretation of this inner product or the complex number Cn is how much of psi, the state, is pointing towards psi n. Remember polarization? And that's essentially the definition of your probability amplitude. Of what event? Occurrence of psi n. So in case of a beam splitter, psi 1 and psi 2, as we said, correspond to the detection in the upper beam or the lower beam. In upper beam or lower beam. Another way to interpret this is a conditional probability. Probability amplitude of getting, so this is a conditional probability amplitude. Which is to say probability amplitude of getting state psi n given the state is psi. So very good. So in general, this was about detection and probability amplitudes and probabilities, but essentially, what is the physical quantity we observe? Something like, let's say, the position or the momentum or the energy. What are the physical observables? Well, physical observables are things like the position, velocity, so on and so forth. And essentially, what values of these observables are obtained upon measurement? So, in quantum mechanics, physical observables are associated with self-adjoint operators, Hermitian operators. Let's say I'll say A. Let me just, so this is a Hermitian operator. And what values of these observables are obtained upon measurement? By values I mean what is the quantity that clicks on the meter. Let's say when you're measuring position, you're measuring momentum, you're measuring angular momentum. So what are the values of these observables are obtained upon measurement? Well, the result of measurement of the physical observables is always the eigenvalues of the corresponding observable. Which eigenvalue? If you can ask. Well, here enters the intrinsic randomness of quantum mechanics, which we've been talking about all along. So, well, if I have an operator A and an initial state psi, the eigenvalues are lambda 1, lambda 2, lambda n of A. I express the state psi in terms of the eigenvectors of psi n, and the probability of the eigenvalue, which eigenvalue shows up, is given by these guys. We are going to see this more in detail in the next lecture, but that essentially is the idea. Quantum mechanics is inherently probabilistic, and what outcome is measured when you measure an observable, that is given by the square of the amplitudes when you express the state in the eigenbasis of the Hermitian operator. And this is known as the Bond's rule, which you already know. And this was seminal work by Max Born, for which he got the Nobel Prize. And interestingly, this occurs as a footnote in his paper. So, perhaps never ever a footnote has got a Nobel Prize, but that's how things are. So maybe when we read papers, we should pay attention to footnotes also. But anyways, we'll continue this next time. Goodbye.